Hello, everyone, and welcome to the second part of the Avalon Holographics webinar. My name is Chris Chinnock. I'm the president of Insight Media and your host for today's webinar. With us today are Wally Haas and Russ Baker. Say hello, guys.
Hello, all.
So in the first webinar, which was on June 3rd, as I recall, they talked about the first three W's of the 5 W's of holographic displays. So today we're going to talk about the second two. There'll be, as we did in the last webinar, there'll be a presentation mostly by Russ today. And then we'll have time. There'll be actually 3 audience polls that we'll do during the webinar, and then there'll be time for Q&A at the end of the webinar. The presentation part will run roughly 45 minutes or so. Does that sound about right, Russ?
Yep.
Okay. So then we'll have time for Q&A. Last time we had a lot of Q&A, so we kind of ran a little bit late. That's fine. We will run a little late if there's still active participation. If you need to get off at the top of the hour, that's fine. We understand. So just a little bit of background before we get started. Avalon Holographics is the leading, the next wave of display technology with professional holographic displays that revolutionize the way people produce, view, and understand visual content. By replicating the experience of looking at real objects, Avalon's holographic displays produce realistic, comfortable, and headgear-free immersive experiences. With a myriad of applications, including medical, defense, and consumer uses, Avalon Holographics is poised to disrupt the industry while setting the standard for holographic displays. So I am not going to, I have Wally's and Russ's bios here too, but I think I will defer on those for the time being and let Russ just get started here. Russ, it's all yours.
Perfect. Thanks, Chris. Hello, everyone. I'll just get right into it. As Chris mentioned, we did structure this as a webinar in 2 parts. So I'm going to briefly review what we went through last time, just so that everyone's, there's obviously a few weeks have gone by, and I just want to make sure it's fresh in people's memories, because it does affect the 2 new topics, which are the where and the when, which specifically relates to markets and timing. So just as a brief summary, what we reviewed in the first webinar included talking about what isn't a holographic display. There's a lot of stuff out there using that term. There's a lot of things that use that term that aren't even properly a 3D display, let alone holographic. But most importantly, stereoscopic 3D technologies really use a trick that convinces your brain that it's seeing something in 3D, but it's not seeing a natural 3D image to focus on. And that's because it's not using directional rays of light. And that is really the key differentiator. We're also not doing what you've seen in the movies with floating light sources, just as a reminder. What we are doing, as I said, is generating directional rays of light. That is the same thing that the human visual system evolved to see, and therefore that is what it is expecting to see. And a well-implemented holographic display will reproduce that in a way that is, if not fully indistinguishable, at least mostly indistinguishable from what you would see if you were looking at real objects. A little consequence of that that's worth remembering is that you're not able to break the frame. So what that means is, like on this example from Prometheus, that tabletop, all the light, except for the portion that's been blocked out in the top, because of course the director loves that effect, is actually coming from the surface of the display. So that's a key, and that's true of all displays of this type, not just ours. We talked a little bit about how you actually build one of these displays and the difference between pixels in a 2D display and Hogels in a holographic display, which generate basically a cluster of rays from a point on the display, and how that translates into a trade-off between viewing angle, depth, and sort of spatial acuity, which is the closest parallel to what people are used to when they think of resolution on a 2D display. I'll cover this more in this session as well, so I don't have to talk about it much here. And there's the so what factor, and as I mentioned already, You know, light fields are actually what we all evolved to see, and all holograms are light fields. So if you can present the human visual system with that natural directional light, then you will perceive it normally without all of the side effects that come along with other 3D technologies, nausea, headaches, fatigue, et cetera, et cetera. So the two things to take away from that, and this will affect when I talk about markets, is there is a proven reduction in cognitive load when viewing holograms. This was studied on printed holograms because at the time there were no digital displays that did this. And we don't need any kind of wearables. And as I said, we do not induce any of those side effects. So I think that brings us to the first poll question. Chris, if you want to jump in.
All righty, let me see if I can launch that. You should see that on your screen now. So what do you believe are the top markets for holographic displays over the next 3 to 5 years? Please select one. And I see a bunch of responses coming in. That's great. Okay. Looks like we're getting close to a stabilization point here, I think. Just give it another couple of seconds and I'll see if I can display this. Okay, let's close the poll. And let's see if I can display this, share it. There we go. Defense and medical and public entertainment seem to be the leaders here. How does that strike you, Russ or Wally?
Yeah, I'd say that's a reasonable expectation based on what we've seen in the market so far. I'm going to talk a little bit about the economics, which may make some of those slightly more viable in the short term than others, but that's generally what doesn't surprise me much.
Okay, great. I'll hide that and let you move along.
Okay, are you seeing my screen or do I have to reshare?
No, we're seeing it. Yep.
Okay. All right, so that brings us into markets. So we kind of look at two big categories of markets. As you'll have seen in both my presentations, I like to categorize things. So the first is, really commercial and defense related. And, we've seen the most interest from defense, medical, industrial, and there's sort of an overarching computer-aided design, modeling and simulation aspect that overlaps these. And the real reason behind that and the real ROI benefit to those markets is cognitive advantage or, cognitive load reduction. So the value proposition in most of those spaces and why it's, defense and medical in particular are a focus area is that you can, save lives or, win battles in the case of defense. And you're looking for really a performance saving of some sort. So there's an ROI to the end users there. When you get into the entertainment and consumer space, there's obviously a lot more variety here, and really the value prop now is just about eyeballs, right? Getting people's attention and doing something they find really interesting and exciting. And if they do, they will, either look at your product or visit your site or your, go try to find your product and buy it. Now, obviously, there's a lot of markets out there for, anywhere you've got a display of any kind, you could imagine you could potentially make that a holographic display. So I haven't covered nearly everything here, and there's overlap, right? Some of these markets, they mix some of this value prop, but fundamentally that ROI is what's going to determine what kind of price any given market wants for the technology, and that's a pretty critical aspect of what we're talking about here when we look at specifically early use cases. Now, we talk a bit about, the markets we're focused in, defense, medical, and industrial, and one of the reasons we see a lot of interest in this space early is there's a lot of commonality. So first and foremost, the data is all inherently three-dimensional. Nobody's actually wanting to wear headgear of any kind. That just happens to be the technologies that are largely available today. You've got a situation where the users might be operators working an entire shift. They want to sit there for 8 hours and use the technology. So if you've got any kind of side effect, that's going to be a major problem. It's not an occasional use. It's not just somebody walking up and seeing it briefly, but it's actually used as a tool for long periods of time. And there's often a need for group communications. So an operator is one of these areas where, if it's in defense, it might be a terminal operator or an expert in a particular field. Medical, it might be a surgeon planning a surgery. They may have a portion of their use where they're doing things individually, but in the end, they're always needing to communicate with someone else, including often people that do not have the expertise they have. So representing things visually becomes really, really important for ease of communication and accuracy. Now, when you start thinking about use cases, again, there's a lot of overlap in these spaces. So one of them we talk about as maybe the most critical is the fact that you're dealing in some kind of real-time decision space. In defense, it's called battle space. It's fair to actually think of it as a battle space in all these domains, in the sense of battle space meaning you're making high consequence decisions very, very quickly, and your speed and accuracy may affect outcomes. So that's one of the parameters we see as pretty important for using this technology as an early adopter, especially. Anything to do with big data analysis and fused data. So anytime you're dealing with huge amounts of data that a human being is trying to comprehend and look for patterns or anomalies, it's really useful if you have a third dimension to represent that data. Throughout my career, I found this problem all the time. I've always wanted like 3-dimensional Excel sheets. I've tried different things with 3-dimensional charts in Excel, which sometimes work, sometimes don't. It kind of hints at the types of things you might want to do with a holographic display. Anytime you're dealing with remote control of let's just call it assets, could be anything from a fighter jet to a tiny drone, or a robotic arm in a nuclear facility, whatever the case may be. The idea being that if the operator feels like they're sitting on the end of that robot and can actually, it's like they're actually there, they're going to control it more efficiently and more effectively. Of course, as I said, anything to do with CAD modeling and simulation, those are all naturally very 3-dimensional visual spaces, and therefore there's always interest from those communities. And the last note I'll make in the use case side, you'll see this come up in both the operational side in terms of actually doing things in the space, but also in training. So there's always a bit of a tension there. Training is often easier or an easier entry point for a technology, but there's no point in training on the technology unless it's used operationally. So you often will see a need in both of those domains kind of in parallel. And again, getting back to the benefits, it's really about cognitive performance. And that's because this translates into faster, better decision making if you're in an active decision space. Or if you're in a learning space, it's about faster learning and better retention. And across the board, you're going to get benefits in terms of alertness and stamina because you're not inducing side effects the way other 3D technologies do. And of course, finally, not only is this applicable to spatial data, so actual representation of 3D physical objects, but it is also applicable to non-spatial information and multi-dimensional analysis. So kind of just a summary of where some of those early markets are. These are, these three that we've shown are not the only markets that have these commonalities, but they're certainly the ones we've been focused on and seen the most interest at this point. Now, in the next few slides, I'm going to go into a little more detail. This is going to come back to the technology a little bit and talk about what it means to actually design one of these displays. Once you get past the hard part, or the first hard part of actually just making it work and getting the kind of pixel density that you need in order to generate, billions of rays, which I talked about in the previous webinar. The next step is how do you use those rays efficiently for different use cases. So you'll recall from the previous webinar, if you saw it, there's actually kind of 3 dimensions you have to play with once you have a set of basically a bed of pixels that generate rays. And the higher the density, the more densely packed those are, and the smaller they are, and the more you have, the more rays you have, the more fidelity and the more flexibility you have to work with in the optical system. But that is a trade-off between the spatial acuity, which is sort of your classic height, width, density. What's the finest thing you can resolve in the space? traded off against the viewing angle, which is how far off of center can you be and still see what the content, and the depth region in the display, which you may recall from last webinar. The optics of any system will give you a region or a volume in which everything is sort of optimal, and you can easily and clearly focus on them. If there's content that moves outside of that boundary, you will still see it, but you may find it softer, it's hard, you can't necessarily focus as sharply on that object. And of course, if it gets too far out of there, it just becomes blurry. So you tend to manage that space, and the more depth you have, obviously, the less you have to worry about that. One of the key points with this technology, and this is really about the physics of the optics, is that trying to get both a lot of depth and a lot of viewing angle at the same time tends to get very expensive. And when I say expensive, I mean in terms of how many rays you have to use to achieve that. And that's because it's a trigonometric function, not a curve, not just a straight line. So don't worry too much about the numbers here, other than you can see as the viewing angle increases, the depth, decreases non-linearly. That's for a fixed number of rays. A way that the way to think about this with this trade-off is if you think about different depths and different viewing angles, it's almost like squeezing together. When you decrease the viewing angle, you get more depth. I think about like squeezing together Play-Doh. And this graphic kind of gives you a little bit of an example of what that looks like.
Russ, what are the three lines in that graph there?
Yeah, so that's just different ray densities. So they're just shown for shape. I wouldn't worry too much about the actual numeric values. So the reason I talked about all that is because when you actually sit down to a given use case and you have to think about the technical fit of what does the display actually need to do for that use case. And it can be challenging for all of us in the space because this is a new technology. People, may have an idea of what they think it is from movies or from, I'm going to say sometimes bad marketing practices from other companies. But in the end, what you really got to understand is that trade-off between those three variables. Now, the idea of spatial acuity is familiar because we are used to resolution in 2D displays. It's not actually the same. It turns out it doesn't work quite the same on a holographic display. Your eyes are actually super sampling the rays coming out, and therefore you're getting better visual acuity than you might intuitively think based on the number of Hogels that are in the display. But nonetheless, it's at least a familiar concept. Viewing angle is pretty intuitive, right? How far off center do I go? Eventually you lose the visual. That's a simple concept. So it's easy to think about, a use case and say, okay, well, I only need this within that viewing range. But the depth is the more complicated thing. And the challenge here, and this has been a real challenge for everyone in the space when it comes to COVID, is you really have to see this live to fully understand and perceive exactly what it means. And it does have some new rules related to how you use the display, although it fundamentally, what the things you do with 3D graphics on a 2D display are still completely relevant, and the content actually often translates directly, but you may want to optimize how you use it in this 3D volume. So of course the challenge is there's actually a per market and per use case answer for every one of those parameters. And you don't want to be going out making custom optics for every single customer. So part of the challenge is trying to figure out where the common landing points are. So when we map the requirements of technology, and again, don't try to read too much into this image here. The main point of that shape is the fact that let's say you have a given number of rays and a given ray density on a display as your sort of, I think of it as a pixel bed that you start with. Then you want to decide where I'm going to make those trade-offs and optimize for each use case. First of all, one of the points of this diagram is to show that if you want to optimize towards your traditional HD or 4K spatial resolution, it's quite expensive. It's using up a lot of the rays, and therefore you get very, very low viewing angles and depth. And I mentioned that super sampling idea behind the way that your eyes sample the rays in the viewing space before, and because of that, it's overkill to actually aim for HD and 4K. People are intuitively going to assume that that is the target, and they're going to probably resist the idea that it doesn't need to be that high. But when you actually start seeing things and you look at the numbers and then look at what you're seeing, you'll find that it is true. And then the three big cases there that are shown is if you try and bias towards any of those targets of, say, a really, really deep field, a wide viewing angle of 90 degrees, or a HD class of Hogel density. And this is for basically like a 2 gig array display. Obviously, if you have more rays, then you can start filling in, all those triangles get larger. But optimizing for just one parameter is generally going to be a major sacrifice on the other two. So you tend to find you making trade-offs in the middle. So in the end, if you want more fidelity than you have out of a given display, you need more rays, and then that translates into the need for higher pixel density fundamentally. And of course, you can also achieve this by having a larger display. And if you know something about 2D displays, the concept is the same, where if you want a large display at a longer distance, it fills the same field of view in your visual region as a smaller display closer up. So if you have a fixed pixel density, you can actually cheat and get more rays out of a system that's further away from you, that's larger. So, but either way, you need more rays if you want more fidelity, is the bottom line. I think the next, that gets us to question number 2 on the poll.
Okay, let me launch that. Which of these sizes would you focus on? You being an attendee who theoretically has an application in mind. So it's kind of a size question here with 17 to 30, 31 to 50, 51, 70, or much larger. I realize not everyone on this webinar has an application, but so you don't feel pressured to vote. That's okay.
Yeah, and those first 4 are really sort of, think of them as flat panel situations versus the last one being, a larger installation.
Right, exactly. Or a tiled solution of some sort.
Yeah. Just a big jump to theater size versus room size.
Right, exactly. So actually desktop to room size, yeah. Okay, looks like we've got a pretty stable vote here. I'm gonna close the poll and share it on the screen. So virtually nothing in the theater size class, which is interesting. It's with smaller sizes here. Is that what you were expecting?
Yeah, I thought there might be more of a mix, actually a little bit based on the previous poll and the fact that there was a number of people talking public entertainment. That's usually what drives those large scale display concepts. But public entertainment is a pretty broad footprint. So, people may be thinking more along the lines of there are installations like at theme parks like Disney and Universal with, a room, and you have a display sitting on a shelf in a room, that sort of thing. So it is, I thought it'd be a bit more of a mix, but it's certainly, that's good to hear that people are generally focused on the somewhat smaller sizes, because that is more easier to achieve in the short term. So.
Yes, I think that's a practical result, what you're seeing here.
Yeah, exactly.
Okay, let's turn it back to you.
Great. All right, so that was sort of a tease or a lead into the next topic. Now there's a fair bit of information on here. I wouldn't suggest getting hung up on the fine details. What I wanted to talk about a little bit is just provide some examples of how these requirements tend to play out. And there's actually, you can see that I've got another half of the screen I'm going to fill in a moment. There's really trade-offs on 2 sort of broad categories here. The number of viewers and the viewing angle requirements tend to be related to the environment. So that again is the difference between sitting at a desktop or a console versus a planning area in a room versus a wall size or conference room display for a bunch of people collaborating, right through to the large public spaces. So you can see here, different scenarios kind of have different requirements, and especially the viewing angle can vary quite a bit depending on how you're going to set up the display and who's going to use it. So that's important to keep track of, because the difference between a 40 to 60 degree viewing angle and a 90 to 120 viewing angle, if you recall that previous slide, it's a lot more expensive in terms of rays, which really just means, you know, if you want to keep everything else at roughly the same fidelity, you need a lot more rays to do it.
Russ, let me just interrupt for 1 second to remind folks, please use the question tab if you want to write some questions to ask Wally and Russ at the end here. I'm sorry, go ahead.
No problem. So that's the, you know, the environment-based drivers for the requirements. The other half of the equation is, you know, really related to the content, and that comes back to both the spatial acuity and the depth requirements. So that is much more application driven versus environment driven. So you'll see here again, you know, these are fairly high level examples of the different application spaces, and some of the requirements, obviously, even within these, there's quite a lot of variety. So you might have a, you know, a defense application that wants very high fidelity stuff, and an easy example of that is a trade show rather than an actual operating environment. But you can, you know, sort of intuit that, you know, the defense folks don't care if the little icon of the fighter jet has all the right textures and looks perfect. They just want to know that's a fighter versus that's a tank. So there's a listing here, and I put little circular arrows at the bottom because once you get into, you know, industrial CAD, particularly on the showcasing side where you actually trying to get people's attention, gaming and entertainment and cinema, there's a lot of overlap in the requirements there. And, you know, cinema is always the one that, of course, has a special case of wanting to take captured 3D filmed content and translate it to the display. And that, of course, is an additional challenge over the, you know, the synthetic data that's common in a lot of these other environments. I'm not going to get into a lot of detail on that in this session because we don't have time, but just be aware of that. The next thing I wanted to touch on is there are some common myths out there that I thought it'd be worth at least giving our take on. And there's really two big ones that we hear, you know, somewhat regularly, and I thought it was worth touching on. The first one is, you know, isn't the stereo 3D stuff good enough? And the answer is, in some cases, sure. There's situations where you're only going to look at the display for a short amount of time. You're trying to just catch people's attention, deliver a bit of information, and then move on. That's probably not, you know, that's probably good enough for that case. Where you'll start to see the pivot point, I think, and you're seeing it now, in fact, with VR, is you know, something like gaming, where somebody wants to do it for an hour, not just 5 or 10 minutes. I personally find I have a PlayStation VR, and I can do that for about 20 minutes, half an hour before I just start feeling you know, uncomfortable. If I push it, then it starts to make me feel a little bit ill. That is individual to some extent. Some people have less reaction than others, but it's a challenge. And part of that is vergence accommodation conflict, the visual system's reaction to stereoscopic imagery. And you know, we personally don't see any, you know, that going away anytime soon. That's probably always going to cause side effects as long as you're dealing with stereoscopic content and images and technologies. And then, of course, the last thing is nobody really wants to be wearing the display. So that is, you know, it's something people will tolerate until there are alternatives available. So we don't see stereo 3D as useful for most professional applications. It is used nowadays, right now, again, because there's really not a lot of other options out there. But we think in both the professional case and even in the consumer case, it'll be acceptable until something better is available, and that hopefully will be holographic displays. The other myth that shows up fairly regularly, especially when you're walking around Silicon Valley and talking to people in the tech industry, is, you know, won't there be AR glasses everywhere in 5 to 10 years, and won't displays just go away? Now, that is, you know, that's a concept you've seen in science fiction movies and shows, and of course it's the sort of thing that sounds great, but, you know, Wally and I have been spending a lot of time on the challenges of making these things work, even when the display is, you know, 2 or 3 feet away from you or more. And that is very difficult alone. But when you try to put the display like an inch away from your eyeball, the scale of the challenge goes up by orders of magnitude. So we're not saying that you won't have AR glasses as a very cool product that will be out there and I think will be used a lot. But I do think that will end up always be a bit of a lower fidelity interface. So It's great for people, you know, walking around town and you get, you know, pop-up information. It can be in stereo 3D, but that stereo 3D, again, because of Emergence accommodation conflict, you don't want to have it up there for long periods of time. You're just going to highlight, hey, you know, here's a street crossing, or you've got map updates as you're navigating the world, that sort of thing. But I don't think that those glasses will ever replace high fidelity experiences for viewers. I don't think you'll ever be able to get, you know, the level of density required 1 inch away from your eyeball, so that experience is so good that you don't need independent displays. Now, I could be, you know, 10 years from now, someone could dig up this webinar and I could be the Bill Gates saying 64 kilobytes is more than anyone ever needs. I'm okay with that if it happens. It means somebody's made some incredible breakthroughs on physics, but that's sort of, you know, our expectation at this point. So now I'm going to talk a little bit about timing. So the way I try to look at this, and, you know, keeping it relatively simple, is you've got this trade-off between the fidelity of the user experience and the cost of the solution over time. So, you know, not getting into specific numbers, what you want or what you expect to see, this is, you know, pretty standard capitalism 101, we'll call it. You expect as you scale up volumes, you can bring the cost down while simultaneously bringing the quality of the solution up. So we're no different in that regard. And I'm going to talk a little more detail about what this means specifically to our space. But first, next poll question, Chris.
Okay, let me launch that. For your desired use case, what's the maximum viable cost range? Now, I realize everyone at Avalon Holographics wants you to say millions, but that's okay. Just be realistic here, because I think they're looking for some realistic feedback here.
Yeah, and this does tie back probably to your answers to the previous question. So if you're in a space with smaller displays, then you're probably going to have a different answer than if you had a preference for larger displays.
Right, exactly. Okay, I see some votes coming in pretty well here. I'm going to close it in just a few seconds. It looks like 70% have voted, so I'm going to close it now and share the results. So I guess that's probably expected, wouldn't you say?
I'm not actually seeing the results pop up here.
You're not sharing? I'm seeing it on mine.
Yeah, I can see it on mine too.
Yeah, I don't know. Maybe it's because I'm still showing the screen.
Okay, well, I'll read it to you. It says 31% is less than 1,000, 47% says thousands, 20% is tens of thousands, and 2% for hundreds of thousands. And sorry, no one said millions.
Yeah, that's not surprising. Nobody wants to pay that kind of money. Okay, no, that sounds about where you'd expect, especially based on some of the other markets and size answers. So that sounds about right.
Sure. Okay.
All right, great. So what I'm going to talk about now, and then the reason that poll question was in place there, is I'm going to talk a bit about the economics of building one of these systems, fairly high level, but it'll give you an idea of the challenges that all of us in the space are facing in terms of making this all come together at a good price point. Now, one of the challenges, of course, you have with displays is there's huge variety in the size of the displays and the quality and the specifications and everything else. So one of the things, in order to compare apples to apples and just think about this in broad terms, is to boil it down to a cost per area, so that at least you get rid of the size as a variable. And if you think about the technology used to build any given size display, if you kind of focus on the same building block, then you can just boil that down to a cost per square centimeter or a cost per meter squared. So being from Canada, we and the rest of the market tend to use the metric stuff for this. So looking at it as a cost per centimeter squared variable, what this graph is kind of showing is, both there's a range of tolerances of cost in different markets. And of course that, that goes down over time. There's an expectation as the technology comes out that the cost will go down. And the biggest emphasis here is, the consumer space is way at the bottom, almost not visible on the graph. 2D displays today cost, substantially less than $1 per centimeter squared. In some cases, 10 to 20 cents per centimeter squared. Video walls are higher. They can go, the really, really high-end ones that you'd see at like CES when they first launch can go as high as maybe $10 per centimeter squared. But when you look at the markets, there are niche applications where the value is high enough to go higher than that. And that's broadly, again, at a rough end level, that's what's being shown here. And then you can map in different technologies that, where they might actually come in when you start deploying them. And I don't get into specifics here, but I will in the next couple slides. The main point being some technologies sort of have a minimum floor as far as how cheap they can become based on the technology itself. And that green line is what you kind of want if you want to get down towards the consumer space. In all these, there's a reference point on the side there. Just a 24-inch display would cost roughly X at that particular price per centimeter square, just so you have some idea of context there. The next, when you think about where those tolerances are, of course, on the high end is really mostly for prototyping and R&D exercises, and maybe some early product deployments where you have a very specific niche that has a high requirement and a high ROI for the technology. If you get down, when products start to roll out and become a little more mature, if you're still up in that $40 to $60 per centimeter squared range, you're really going to be limited to niche markets. There are markets out there, and I believe there will be success in those markets because holographic. The idea is there's a lot of obvious benefits, and there are scenarios where it's worth quite a bit in terms of ROI. But of course, where everyone really wants to get is down into the same domain that we have for 2D displays. Maybe not down to the same price points, but at least the same order of magnitude. So next slide is, again, this may be controversial in terms of people may have different views on this. I'll caveat the whole thing by saying, we don't have the market cornered on smart people. There could be a lot of innovation that helps change these variables, but this is sort of a rough-in of what you could expect the cost points of these technologies to be over the short to medium term, at least, barring huge innovation or a huge change in the market. And one of the challenges is you'll see a lot of people that will use micro displays to implement holographic displays. These are primarily used right now in VR and AR. They're basically very high density, very small displays. There are some real challenges in putting them together into a larger display because they don't just tile up, and you can't, they have extra circuit board around them. They don't easily tile together, but people have done it and people have made them work. The challenge is that those things tend to be quite expensive on a per centimeter squared basis, and I've tried to show how they would reduce in time over some range, but I would still expect them to stay in the hundreds of dollars per centimeter square range, in part because they're built on a silicon backplane, and the economics of doing that, there's a number of reasons why it's tough to get that down to much lower costs. If people start making them by the trillions, that might not be true. But this is kind of how we see it in the short to medium term. Projectors, our prototypes actually use pico projectors. Those are a lower cost point, but they are still, there's probably a floor to where those can go as well. Maybe it's sub $100 per centimeter squared, but it's not dramatically below that. And then you've got your video wall and flat panel, your existing markets, which, as I kind of showed previously, go from tens of cents to $10 per square centimeter. So where you'd like to target a flat panel technology that does holographic display would be somewhere in that, a bit higher than the flat panel market for 2D today, but still, getting close to there. So when you think about this market and the evolution of the market, there's some useful analogies out there, things that have happened in the past that people are familiar with, and you could expect this to kind of follow a similar trend line. The emergence of 2D flat panel displays actually started in the 80s. The US Air Force, we've actually met the guy who bought the very first one of these for fighter jets in the 80s, and his joke was always, 20 years after we buy them, you might buy them in Best Buy, and they actually bought his first holographic display technology in sort of late 2000s, and so you could argue that the 2020s is when this stuff should show up, and we like that argument. Another analogy that's actually fairly useful is 3D graphics. So those of us of a certain age will remember silicon graphics, and that used to be big machines that did very rudimentary 3D graphics for a huge price tag. And now you can buy an incredibly powerful GPU from NVIDIA or AMD that you just put on your desktop. So that kind of scaling. And you see this every time there's a next generation of TVs that come out as well, right? The very first 4K TVs you could buy on the market cost like $100,000, but within a year or two they scale down to something you can actually the average person can afford in sort of low thousands of dollars. So that's what you should expect to see as this market matures, is those types of translations. So getting back to this graph again and just talking about timing the market, or timing when things are going to happen where, we see it as the first phase is these very high value applications can tolerate those higher prices, and we'll be doing low volume engagements in that space, and I expect to see that from anyone that's entering this space. The second phase, you get into a viable commercial ROI at the price points shown, so you can actually start scaling out into the broader industrial and commercial space. But it's really now that third phase. If you want to get into the mass market, you got to get down to those lower price and cost points, and that's going to take a while. It's always a mistake to put firm numbers on a presentation like this, so I intentionally did not do that. But we kind of see this graph playing out over the course of, say, the next 5 to 7 years. So you would expect the mass market stuff to really start to happen, into the back half of the 20s, so 26, 27, and on. So in conclusion, there are a ton of opportunities and a ton of markets for the tech. When you look at what's going to happen when, it's going to be really a price point and fidelity combination that's going to determine the timing. And I haven't even touched on it in this presentation, but there's also the rendering tech that has to scale in parallel to that, particularly obviously for synthetic information. But rendering could just mean encoding when it comes to captured content and captured light as well. So if that doesn't scale, then who cares how cheap your display is if it needs a rack of GPUs just to drive it. Off-the-shelf technology can support some of these segments at modest volumes for now, but really the scalability of your underlying technology bed is going to determine how far you can go down those paths. And we're at that stage for everyone where people have prototypes and are starting to engage with the market to come up with minimum viable products and find product market fit. For Avalon, we've had our first prototype for over a year now. COVID did slow us down a bit, but we at least have some of those engagements and feel like we're well on our way there. And I think you'll see other technologies, following us down that path. So really the long game for everyone, we think, should be to get this to the kind of scale that will allow you to at least enter the consumer market. I wouldn't expect every display to become a holographic display, but you can imagine a pretty, a good chunk of the top end of the market could transfer into holographic displays because of the, essentially it's a new compelling visual experience. So I'll finish similarly as I did to the last webinar. When you're looking at these topics, kind of ask yourself, how often do I use 3D visualization? What problems do my 3D displays cause me right now? And how would a better display help? So when it comes to how often, why aren't you using it more? That could relate to the next two questions. How could they be better? And really, what's the ideal solution? So when it comes to, how can these things help you? Well, I mentioned it already, decision making. Making faster, better decisions and higher quality decisions with less errors is really the name of the game at this stage. And using that to achieve objectives more quickly. And this, again, in medical and defense tends to be about competition with an adversary, where the surgeon's adversary is disease, typically, or maladies. And in an industrial space, it's actually design challenges. And in the end, it's about saving time, money, and lives. So that's really what this tech is going to be, focused on, I think, we believe, in the next couple of years. And that's where our focus is. So just to sum up and finish, we've actually, I mentioned we've had our ProMax display out for a while now, and we've actually just finished up a roadshow. We finally had some vaccines and we're able to get out on the road and do some demos in a few cities. We'll be doing more demos and trade shows in the next 6 months. So if you want to stay informed on where we're going and where we're demonstrating, please do register at our website and we'll keep you up to date on that. Of course, you can follow us on LinkedIn. We do announcements there as well. And you can also feel free to reach out directly to me or anyone else at the company if you have any questions or anything you'd like to find out. And I will jump back to here. And that's it, Chris. So
all right, that was super. Thank you very much. So actually, let me ask you the first question or two here. So you mentioned ROI, right? It's saving lives, saving money, and faster decisions. All of that needs to be validated, seems to me. So you mentioned there were some studies done on film-based holography to show that you could reduce cognitive loads. Are you working with customers or considering developing new studies to prove the benefits of holographic displays now that we have better devices?
Yeah, absolutely. We've actually already had a couple projects funded for that exact purpose. The level of funding was enough for more qualitative studies at this point. We haven't done what I would consider to be a formal human factors study yet, but we're looking for a partner to do that with. We have a lot of number of candidates that are interested. So we do expect over the, I'd say the next year and a bit to come out with some results that are done on a proper, dynamic digital holographic display instead of the still print holograms.
But to just add to that, like we have done those qualitative studies, and the still print hologram showed a 30% performance improvement, sometimes higher. And the qualitative studies that we've done showed at least that percent improvement. Sometimes the task was unable to be performed in 2D, whereas the participants were able to perform the task in 3D.
Yeah, okay. So far all the results have tracked very, very well and maybe even been better than we saw in those still print studies.
So how do you actually measure the quantitatively the cognitive load reduction? Is it just faster doing the task, being able to do the task? Are there real metrics that you can put into these studies?
Yep. So actually, even those still print studies are good reference points for that, because the cognitive assessment doesn't really change much based on the technology you use. So there's really two approaches you can take. The most common one, and the one that was used in most of those studies, is to measure outcomes. So you measure you define performance in the task, and you measure a control group using a different, basically today's technology, and then you do it against the holographic technology. And performance for a decision-making process like mission planning would be basically some combination of accuracy and speed. So they would just measure for different participants how fast were they able to plan a route and how many mistakes did they make, and compare those outcomes. When it comes to training or learning, it's usually about how fast you absorb the material and how well you retained it later. That's like one of the most common ways to measure this stuff. So in a sense, the cognitive load benefit is inferred from that. It's not that you're measuring it directly, because that's challenging. There are some researchers doing work where they're trying to measure that stuff more directly by using things like EEGs and fMRIs. We've had discussions with them, and we may try to do a study with one of those groups in the future, because I'd be very interested in seeing that result. But it's obviously a little more complicated to set up, so that's essentially a more expensive study to do. But that is the other way that this stuff can be analyzed.
Okay, no, that's great. Yeah, I think everyone's going to want to see that kind of data, I would suspect, to make decisions on up the tree.
Yeah.
And then there's the kind of the second piece of that is, once you have a holographic display, how do you measure the fidelity of that display? I mean, you talked about those parameters, but specifically kind of measuring the depth fidelity. We don't really have good way to do that today, do we?
Yeah, it's a little tricky. So, Wally, I don't know if you want to jump in.
Yeah, sure. So there's a couple of issues that are kind of rolled on into one there. There is a simplified equation that you can use that we're actually making a what is a hologram video, and we'll be sharing it there. But it's available in the literature that talks about how you can measure depth given a certain optical system. So that is a very good sort of rule of thumb. It's actually much more complex in order to try to actually understand the fidelity, and as Russ talked about earlier with the super sampling. But in terms of sort of a back of the napkin estimate, it's perfectly fine and you can use it. But as for how are you going to measure the overall fidelity, including the super sampling, that is a more difficult problem. And even though we've kind of looked at it and tried to figure out the right way to do it, it is somewhat specific to content, viewing angle, distance. So we haven't come up with a sort of a catch-all parameter other than what we've seen so far, which is just put the experience in Hogel's sort of width, height, and depth, because that does provide the correct relative experience in the same way that a HD resolution on a small phone at a certain distance gives you the same experience as a larger HD screen from a longer distance.
Right. I mean, can you characterize the depth fidelity by just kind of thinking about it as resolution at different planes, different distances from the plane? No.
The problem is that when you think of directional rays, there are no longer planes. You have to integrate through the entire volume space. So to think of it as, oh, I'm just going to measure fidelity at this plane, then this plane, then this plane, then this plane, then you are negating the nature of the holographic display and holograms in general by ignoring the ray-based nature of them. So no, you cannot look at it from a singular planar perspective.
Yeah, what you probably end up needing there is a way to, and this actually happens. It's very similar to what they do when they judge compression algorithms. It ends up being subjective, so you have to kind of get a study where enough people observe it and can essentially measure what their visual acuity is, which is to say the precision with which they can estimate a given size of object in the space, and then translate that back to the 2D equivalent, right? So you'd be able to say, this layout, regardless of what the specs are, is in approximately equivalent to what you'd expect from HD or whatever the landing point may be. But we still have to work that out.
Yeah, that's okay. I like that. Complex, but a good challenge. All right, let me turn to some of the questions here. So Phil asks, can you speak to the trade-offs such as spatial depth perception between your holographic display versus those newer super autostereoscopic non-glasses displays, i.e. 4K and 8K lenticular lens displays?
Wally, you want to do it or should I?
Yeah, sure. So the problem is that you're comparing apples and oranges. When we think of those super stereoscopic displays, you're creating a situation of effectively slices of light. And so therefore you're going to have a Emergence accommodation problem. So if you look at a slanted lenticular display from a certain distance, and then move your head up and down, the whole object is going to sort of rotate and swim with you, which is an immediate sort of physical understanding for you to see that you're having Emergence accommodation conflict, even though you are having it, period, even though you might not be able to kind of immediately perceive it. And you could do the same thing by walking towards this display or walking away from it. The object will just sort of swim towards you. So in terms of the visual acuity, you can't really compare something that has a slanted lenticular that is effectively sending out slices of light versus the individual ray-based approach that real holographic displays have.
Yeah, no, one thing you can at least compare, it's not apples to apples, but it's at least in the same ballpark, is the sort of optical calculation of what the depths for the display types are, just from the convergence of, in their case, it's the light slices, and ours, it's the rays. So you will see in some of the tech that's out there now, you know, they're getting, depending on which specific instance it is, something like anywhere from 2 to 4 inches of sort of effective depth regions. Total, that's in, you know, the combination of the in and the out of the display surface. And our first prototype is about 6 inches, but it's a lot more rays, and you know, it is more expensive. So that's you know, not surprising it would have higher fidelity there. So at least in a first order understanding of what you're getting as a workable volume in those displays, that is what you're seeing. The guys at Looking Glass have talked about that viewing volume in the same way we do. Where you can just kind of make it a ratio of the width to the height to the depth. And so I think their portrait is something like 3 to 4 to 2 or something along those lines, which gives you a sense of the shape of the volume. And it's in the, you know, so we're a little bit deeper than that, but kind of in the same ballpark.
Yeah, but our display is much larger, right? That
Yeah.
ratio does not hold for larger displays.
Yeah, so it doesn't translate directly, unfortunately.
Right. Okay, Bill asks, how did your road show go? Any interesting learnings?
Yeah, we learned a few things. We learned that UPS is not as gentle with their equipment as we had hoped. So we had to do some emergency calibration over the weekend. But that, you know, Wally was a trooper and stared at a screen full of bright stuff for a while, and we got it done. But get it, you know, back to in terms of the demos, we did have, you know, one of the things we've seen is we've had pretty universally positive reactions from everyone that sees the display, because it is something new they haven't seen before, and they sort of, until you see it live, you don't fully appreciate that it is a new experience, but everyone gets it, which is great. I actually anticipated when we started doing demos, there'd be some portion of the audience that might be like, my PlayStation looks better than that, but we haven't had any of that. We had some very good feedback from experts in the field at the academic level who have done work in holographic and light field displays before, and gave us, you know, very strong kudos, saying, look, I know how hard this is, and you guys have done an excellent job, so you're well on your way. That was very nice. Learnings from the customer base, I'd say reinforcement of what we already kind of knew. We have a lot of engagement on, you know, both defense and medical, and the people we're demoing to are largely already on board and understand why they like it, and this was just reinforcing that, you know, they really see that now that they've seen, the ones that hadn't seen it live before, just, you know, confirmed they were very excited to see what they can do with it. So.
Yeah, and the kind of range of responses that we get are anywhere from, oh wow, yeah, that's something I've never seen before, all the way to, that is practically the most amazing thing I've ever seen. And you generally, it's those people that have the high visualization need that tend towards the, oh, that's the most amazing thing I've ever seen, because they can immediately understand how this is going to be useful in their end application. In terms of what to improve, right? Like, this is a prototype. We've had some artifacts that you can kind of see with the display, but it's always, hey, can that display be bigger? Can it have a higher viewing angle? Can it have more depth? Right there, like, these are things that are inherent to any sort of holographic visual experience. You just want to hit the more button in all three areas in order to get the kind of experience that you want. And like our prototype display has hundreds of millions of rays, but we know that you have to be in the billions of rays in order to actually sort of satisfy the customer expectations, and that's where we're going.
Well, actually, then that's a good segue into my next question. Since you are at hundreds of millions and you said you need billions of rays, how do you get there? What's the technology path for you?
It's a combination. I'll go, Russ. It's a combination, and Russ talked about it in his presentation. What you need to do is this first prototype that we've shown is based on projectors that came out of AR glasses. So while the highest density that you could buy commercially, it's not the highest density that's possible. So we're we've created a system that allows us to get a much higher density of individual rays, and we've created a system that allows us for it to scale into a larger array. So that's how you get to sort of billions of rays. And then we've got our own proprietary compression system on how we can control that in real time for the markets that need it. As for our long-term solution, we know that we need to get down to sort of flat panel style pricing, and therefore we're working on flat panel style technologies, but we're still a few years away from getting that to market.
Okay. Let's see. Joyce says, what are you doing to support content creation?
Yeah, I didn't have a ton of material on that in this presentation. I may have mentioned it a bit in the previous one. So we've got kind of call it a multi-pronged strategy for that, but our opening efforts are really focused on two approaches. One is if you've got an existing 3D application that is in-house and you have access to your own source code, there is an API and SDK that you can use to kind of integrate that directly so it'll drive the display. Whether, depending on the performance requirements, or the performance requirements will determine, whether you do a light or deeper integration effort there. There are a lot of use cases where you don't need sort of, 30 frame per second fully interactive, and therefore you can make a simpler integration. But then on top of that, we're actually doing initially integrations with a number of applications where we have access to source code. So the gaming engines are the most obvious platform for us because they do offer a ton of tools for not only their own use, but also for pulling data in from other tools like CAD tools and production tools. So we've got an Unreal Engine build that's sort of in alpha state right now, but that'll be available to customers shortly. Where basically, if you have an Unreal project that you've already developed or you're developing one, you can pull that in to our environment very, very easily and use it. We're also under contract now to do a Unity build, which will be probably towards the end of this year. That'll be available. We've done work with some other select tools. VTK is a fairly common visualization toolkit that's used in a lot of things like ParaView and 3D Slicer, which is a medical tool. We worked with a platform called SIMDIS from the Office of Naval Research in the US, but it's a government off-the-shelf tool that a lot of defense parties in NATO use. So we've got a smattering of other support in there, but gaming engines are actually probably the best fit for early development work because they're already very full-featured. We already have the integration done, and as soon as you can get content into that space, you're ready to roll.
And that can support interfacing and ingesting MRI and CT data as well, those tools?
Yeah, there's already some plugins and support in there for pulling that data in. The range of tools available from the medical community, there's quite a few different ways of getting that data in. So it can be done through Unreal, it can be done through 3D Slicer, which is the other tool we've already done work with, and there's a few tools out there.
Okay. Okay, Gene, hi Gene, asked what tech are you using? I think you've kind of mostly explained that already, don't you think?
Yeah, projector-based is our current platform. We've used Pico projectors. They were actually the type that were originally designed for being in the earband of AR glasses, which is why the form factor was convenient for us. But our second gen, as Wally said, we'll actually assemble our own so we can pack them as tightly as possible.
That would be great, and higher fidelity, I presume. Do you want to put a ray number on that yet? Yeah,
so the current target spec is in the 50-inch diagonal square. It's about 1 meter or 3 feet square, and it is on the order of 7.4 gigarays, so 7.4 billion rays, which works back down to somewhere on the order of a 10 micron equivalent pixel size.
Wow, that's going to be awesome.
Yeah, it should be impressive, and we get rid of a lot of the artifacts because now that we've taken charge of the modules themselves, it's a lot easier to make everything mesh cleanly. So we're expecting that to be a pretty incredible user experience. And just as another data point, with those billions of rays. We make the viewing angle wider, but we're also getting about 18 inches of depth now.
Oh, wow, that's significant. Yeah. Yeah. What's the time frame for a first prototype?
It'll be in the lab back half of next year, and then productization follows. So I'd kind of assume we'll be getting it out the door in early 2023.
Okay, great. Samuel, hey Samuel, says, what will the solutions for capture 3D scenes for entertainment applications? What will be the solutions for capturing 3D scenes for entertainment applications?
Yeah, there's I'll try to keep that at a somewhat high level, but there's kind of two pieces to that. The first is capture itself. So obviously, wherever you're filming, you have to be filming it in a way that allows you to extract 3D information from the scene. Fortunately for us, a lot of that is already being done. Seeing that used in things like sporting events where you have multi-camera viewing that is, through software being translated into 3D models, which can then be used for things like instant replay, and they'll have virtual cameras flying around the arena and things like that. You've also got volumetric capture going on, so people are building volumetric capture stages and studios. And I just talked to a company the other day that's doing, smaller form factor kiosks for things like, putting it in a store for you to virtually try and close, that sort of thing. So some of that's being solved already, and by the time we're in a position to take advantage of it, we expect that some of those capture side things to be fairly mature. So option A is render the, actually have that captured content translated into a renderable 3D model space, which means the tools we have already are just there to use it. The other side of the equation is if you're actually capturing, very high fidelity, like say on a sound stage, you're capturing a light field as opposed to, just a few camera positions and turning it into models. And we know how to process and handle that data set as well. It's a massive amount of data on the capture side as well as on the display, the raw display side, obviously. If you're familiar with Lytro, they actually built I call it field artillery, a giant camera with a 1.5 meter CCD and huge cables that came out of the back. That gives you a sense of the raw light field capture side. But we do have codec architectures that allow us to dramatically compress that information, and that would you'd want it to be done right at the source and then decompress right at the screen. So there are ways to do it. We're kind of leaving that as tomorrow's problem, but there is a path there.
And just to note, Charter and a bunch of companies did a demo with a 100 camera capture back last fall, which was processed and distributed to a light field display today. I mean, it was still high bandwidth. There's no doubt about it. So there's a lot of problems to solve, but the capture technology is definitely coming along.
Yeah, exactly. Frankly, I expect the capture side to be, it's evolving at its own pace. So we'll probably be able to piggyback whatever state that's in when the time comes. And what will be different will be the essentially the fidelity and density of the target displays. They'll go from the current, half holographic, half parallax display technologies to truly holographic with, another order of magnitude of rays involved.
Indeed. Moving on, Dieter, can or would you elaborate on the technology you are using for your displays, thanks to Advance? I think you've covered that at this point, right?
I think so, yeah.
Yeah. Robin, what angular resolution is required for a seamless viewing experience, the angular equivalent of to 30 pixels per degree, for example?
Well, you want to grab that one?
Yeah, I'm just trying to think of exactly. So I'm not sure if I would follow the exact numbers there, like 30 pixels, 30 rays per degree. You're looking at 0.03 degrees per ray. That's certainly a lot less than a lot of the literature kind of says. In order to get a smooth viewing experience, it's actually more about the directional resolution that comes out. So you have to have a directional ray, and the full width half max needs to flow into the next ray, right? Like they're not individual rays, they're waves, and they have a certain spread. So your point spread function needs to align with what your angular, what your directional resolution is. So I forget the author, but they theorized that around 0.3 degrees was the highest sort of directional acuity that you could get, but anything less than 1 degree per ray, as long as your point spread function makes a smooth viewing experience, is pretty good. But obviously, the more the better, and the higher your directional resolution, the more depth you get. So hopefully that answers the question that the person posed.
Yep.
Yeah, and that's from the display out. That's sort of the angular pitch between the individual rays coming out of the display. Obviously, when you turn that around and look at where the viewer is, there's a certain dependency on the viewer distance as well. So, a large display at a longer distance, those parameters change. But for the use cases we're talking about, where you're kind of within a few meters of the display, it's those somewhere in the less than 1 degree, ideally, in the half to less than a half degree range is sufficient.
And he kind of had a follow-on question as well about, can you actually show infinite distance behind a holographic display?
No. Like you'd have to have a Hogel of infinite capability, right? Imagine a window, right? Like the way to see infinite distance in a window is you have to have infinite rays coming through an infinitely small spot. Now, of course, I'm talking about the most mathematical case. You have a certain visual acuity at a certain visual distance. So of course you can create a perception that is indistinguishable for a human to be able to perceive an infinite distance. But that relates to a number of factors. Just as I talked about before, how there was a sort of simplistic equation that determines depth. The content, brightness, distance, angle all make a big difference in terms of perfect visual acuity for an individual pinpoint observer.
Yeah, no, that is a little ways down the road. You need very, very small pixels and a huge ray density to kind of get to that point from, let's just say, a desktop or room viewing scenario. The other thing, there are a lot of ways you can sort of adjust for that. One example is they actually do this for different reasons in rendering with gaming systems. You can billboard the deep distance in the scene, so it's essentially it's almost like a diorama. It's a flat 2D backdrop, and if it's far enough back, it doesn't matter that you're not focusing on it as 3D objects, because it's you're getting close to where you're not going to get value from that anyway.
Right, that makes sense. Turning back to the codec you mentioned for compression, are you doing or thinking about doing any standardization work around that, or keep it proprietary?
Right now, I would expect us to keep it proprietary. The reason is because the application that hosts the need, basically what the user is going to do, the computer is co-located to where the display is, so there's no need for standardization of that compressive algorithm. We do expect to participate in the standards later on as each of these compressive algorithms for the individual use cases move forward. But the way that you want to do compression is different depending on the use case. So stuff like meshes, you'd compress much differently than you'd compress volumetric data versus static video, like pre-computed, but still extremely high quality video, like a film or a show. You'd have a different type of compression versus sort of an interactive application. So we're not participating too much in the standards now. I know that we have an eye out to them, and Russ has been quite helpful, I think, to a couple of groups, but there's no impetus right now for us to share too much about that codec.
Yeah, and this can be a whole discussion topic on its own. So I do sit in on some of the standards discussions, and there's a big jump point between multi-view displays, which are still fundamentally dealing in stereo images, and ray-based systems like ours. So no matter what, you're going to have different implementations when you cross that boundary, and standards may evolve to try to package that all up in a way that's consistent, so everything can, pull it, you pull the display and figure out what it is, and then present it with the right data. But it's a bit early for that to get standardized until there's, multiple solutions out there and people have implemented, basically tried different things and figured out what works best in different scenarios and use cases, and then boil that into a standard. So I suspect a lot of the standards work for and up front will be focused on, how do you package this stuff and let everything at least handshake well, so that then, whatever implementation of codecs and transmission protocols is required can be, facilitated by multiple users.
Yeah, that would be my summary of what's I think is going on in the standards group too, because I participate in some of that stuff with you as well. So let me, we're kind of at the end of the questions here. I just got maybe one closing question for you. So in terms of processing, GPUs, CPUs, SoCs, FPGAs, what's needed? Do you see the roadmaps for those technologies being sufficient at this point to support high fidelity holographic displays?
More everything.
Yeah, so like we've known for a very long time that we need to kind of fit into the ecosystem as much as exists and as we can. So the way that we've are moving forward with that multi-billion RAID design that's coming out, it will be driven. It can be driven by as little as one GPU, but at most 8 GPUs. So there's not a situation like Russ referred to as you need a room full of GPUs all streaming massive amounts of data where you have to get the entire scene coordinated between all of those different GPUs. So it's really the compressive algorithm that is implemented in FPGAs for us that does really the heavy lifting from taking that compressed algorithm and do all the compression within the GPUs, and then we decompress it right next to the display. But we certainly know a lot about how that compression works. And there's certainly ways to significantly reduce the cost of that over time, just through normal semiconductor technologies. But the roadmap right now for silicon is perfectly fine. We can get these multi-billion RAID designs with the technology that's out now or out in the very, very near future.
Yeah, just to expand a little on that, we do leverage GPU capabilities, especially regarding ray tracing. It's easy to think of the fact that we're generating rays means just keep ray tracing through the screen, and that's sort of the way you actually calculate at a very simple level. So we're able to leverage ray tracing capabilities that are in existing GPUs, and therefore the GPU side of that equation scales almost the same as it would for a 2D scene. The more complex your scene, the more complex the textures and everything else will tend to determine how much GPU horsepower you need. There are things that would certainly help along the evolution of GPU architectures, like a lot more direct bandwidth access to the inside the frame buffers, and just moving data around more aggressively is the sort of thing that could help. But we're not planning to require anything that's not already in the roadmaps of the various companies out there. We're just building on what's there.
Well, some of those capabilities are going to be and will exist in edge-based and cloud-based server architectures. Can you leverage that technology and basically stream something to a display?
It's really about bandwidth. And so, yes, of course, if someone has a 100 gig connection or embedded 40 gig, then these are the kinds of thing, or 800 gig. These are the kinds of protocol technologies that can be used. But again, even at 400 gig, which is as far as I know, the latest Ethernet standard, when we talk about a multi gig array design, you're talking terabits per second. You are still in a high level of compression that is required. So it's not it's not by plugging in a bunch of 100 gig cards you're solving your problem. If anything, you're making your problem worse, because the Ethernet protocol, you'd have to layer timing on that, and coming from the telecom world, that's not something you want to do if you want that connection to go fast.
Yep. Okay. Okay. We are out of questions. I'm out of questions. Well, I'm never out of questions, but I'll stop there. Wally and Russ, thank you so much. And you participants on the webinar, thank you for your questions. We will record this, and I'll send out a link as soon as it is finished processing. Thanks again, guys. Have a good day.
Great. Thanks, Chris. Thanks for hosting.
Bye. Thanks, later. Bye-bye.